Okay, so graphs of exponential functions. Now, exponential functions, if we're not looking at shifts and dilation, so if we're just looking at the basics, it will always, well, most of the time it will cross 0, 1. Reason for that is if you put anything to the power 0, it gives you a 1. Now, if you have any bases that are higher, you might notice that it goes a little bit thinner, like that. And one of the main things that we have to do is we have to find a point, just a point, of an exponential function, and we write down what that point is. So if you have a look at y equals to 2 to the power of x, you have to put down the point 1, 2. If you look at y equals to 10 to the power of x, you might put down 1, 10. Now, this isn't always true. If you have something like an x-intercept, then obviously you would change it so that you put in the x-intercept. But the reason why we put those points down is because we don't always have an x-intercept. So if you don't have an x-intercept, then put in one of the points. The general form of an exponential function is the same as what we've been doing before. There's nothing that's different except for one little thing. So A, capital A anyway, is dilation. Whoops, that should be in brackets. N bracket x minus h. Well, same thing as per usual. H, K are your shifts. N, so 1 over N is the dilation parallel to the x-axis. So this should say dilation parallel to y-axis. Now, you might notice there's a small a there. This is the base, and it actually doesn't matter what number we use for that. You still draw this out in the same way, unless you have to draw multiple ones on the same graph. Okay, so let's just have a look at reflections. I'm going to draw 2 of these out. There'll be a reason for that, and it will become clear in 1 second. Now, if you have a negative reflection, so I will pick green. So if you have y equals to negative 2 to the power of x, negative in front of the 2 means it's a dilation on the y, so that means we're reflecting it in terms of y, thus it will go down to the bottom at negative 1. So if you have a negative in front of the x, as in y equals to 2 negative x, then it will go the other way. Similarly, if we have both of those negatives together, what color haven't I used? Grey apparently. Oh, that's an ugly grey. Anyway, you have negative 2, negative x. Alright, on the same set of axes, sketch the graphs of y equals to 5 to the power of x and y equals to negative 5 to the power of x, stating their range or ranges. So it will be the same as before. You have y equals to 5 to the power of x, like that. And then negative y, negative 5 to the power of x, because that's negative in front of it, that's a dilation to the y-axis, so then it goes downwards. So let's write down the ranges. So range of, and I'm going to be lazy here, I'm just going to label them. So range of y1 is equal to, if you have a look, it goes from 0. Now it never actually touches 0, so you need a circular bracket, and it goes to infinity. Range of y2, similar thing, but you might notice that it goes down to negative infinity, so that'll be the lowest point up to 0. Okay, B. Give a possible equation for the graph shown. Now, you know it goes from 0 to 1, however, you might notice that it's reflected back towards that way. So what that means is you actually have a negative in front of an x, so n is going to be equal to negative 1, most likely. Then, when you put in negative 1, you get a 5. So let's have a look at how that works out. We have a power of something that we don't know. We put in negative of negative 1, and that gave us a 5. So a to the power of 1 gives us a 5. That means a must be 5. Thus, we have 5 to the power of negative x. If you're a little bit lost, I wrote down n equals negative 1. Remember, n is just a number in front of an x, so from here you can actually just write down y equals to a to the power of negative x. Then we just have to figure out small a. Okay, sketch the graphs of each of the following and state the ranges for each. Alright. So a, we have 2 to the power of x, but it's shifted down by 4. Now, one of the things that I didn't exactly mention before is there's an asymptote on all of these exponential functions. So, whatever this value is, that's also an asymptote. So negative 4. Then we just draw in the 2 to the power of x. Now, we need to actually manually find each of the points, so let's look at y equals to 0 first. X equals to 0 first, as in a y-intercept. Then y is equal to 2 to the power of 0 minus 4. That's 1 minus 4, giving us negative 3. So this point here is negative 3. The other one, you have y equals to 0, so then 0 equals to 2 to the power of x minus 4. Rearrange it to both sides. So negative 2x equals to negative 4. Get rid of the negatives. You have 2 to the power of x equals to 4. Thus, x must be equal to 2, because 2 to the power of 2 is 4. Okay, B. So y equals to 10 to the power of negative x plus 1. Now the negative's in front of the x, so we know that it goes this way. And there is a horizontal shift, so that means our y-intercept is going to be different. So let's just find this y-intercept. So x is 0 at that point, so we have y equals to 10 to the power of negative 0 plus 1. So that's 10 to the power of negative 1, which is 0.1. Or 1 over 10, whichever one you like. Sketch the graphs of each of the following and state the range. It's the same as before, we just simply put those in. Y equals to 10 times 5 to the power of 2x minus 1. Now, remember to factorize this first, so we have 10 times 5 to the power of 2, x minus a half. If you factorize it, you can then look at the shift. I know in terms of what we're working out, it doesn't matter so much, but you might need to be careful because sometimes the shift ends up being positive, depending, or negative, depending on what you have. Okay, so this number is positive, and this number is also positive, so it goes in the normal way. There are no vertical shifts, so we can just draw it, and we simply have a y-intercept to work out. So let's put x equals to 0 in again. I'm going to use the original equation because it's a little easier to look at. Wherever I see x, I'm going to put a 0 on, so that's 10 times 5 to the power of negative 1. But remember, 5 to the power of negative 1 just means it's 1/5. So then we get a 2. Okay, y equals to 1 minus 3 times 2 to the power of negative x. Okay, So this is actually a vertical shift of +1, and then this part tells us that it's going to go to the bottom, and this part tells us it's going to be reflected along the y-axis. So the shape will start at y equals to 1, and then it will look something like this. Now, the only issue is we don't know if it's going to pass the origin. So we need to work that out first before we can draw it in. So let's have a look. If x equals to 0, we have y equals to 1 minus 3 times 2 to the power of 0. And as suspected, this does not actually go past the origin. It actually goes to here. So what that means is, because we're starting from here going down, oops, completely missed a point there, we will also have an x-intercept that we have to work out. So work that's -2. Let's work out a y-intercept. X-intercept. So we have 0 equals to 1 minus 3 times 2 to the power of -x. -1, -3 times 2 to the power of -x. We have 1/3 equals to 2 to the power of -x. Now, we haven't done logarithms yet. If we have, I can show you a technique to work out what this is. Actually, we have done logarithms, we'll know about it. So now, because you have done logarithms, we have to take the log of both sides, or you can rewrite this in terms of a log. So you have log of base 2 of 1/3 gives us -x. Whoa, what happened there? Gives us -x. So then x must be equal to negative log of 1/3. However, 1/3 gives us negative log 2 of 3 to the power of -1, which means we can take the negative outside, so we have log 2 of 3. If you're asked to leave it in exact form, that's what you would leave it as. Otherwise, you would normally be asked to answer it in decimals.